Entropy? Average word length? Redundancy? What the hell kind of words are these? They're not so bad actually, and you're definitely gonna wanna learn about these things if you're dealing with data compression. So stay right there. Okay, so let's start with entropy. What does it mean here? The term is used in a bunch of different fields including physics and sociology. In information theory, you know what we're learning right now, entropy describes the average decision content of a code. Or you may be more likely to learn it as the code's average information content. Entropy in this context is often represented by what looks like a capital H. Well, that explains it all. Thanks. Nah, to understand all this, let's first take a look at the formula used to calculate entropy. We all know the sum symbol, right? The P describes the probability that a given character will appear, and the X represents the decision content of a character. So basically, for each character that appears in the message, you look at its probability and its decision content. Then you put it all together to figure out the entropy. Let's pick apart that formula one more time. Right, now what's PA gonna be? Well, let's have a look at our message, why don't we? A appears 4 times in a total of 8 characters. That means P of A is 50% or 0.5. B appears twice, which gives it a probability of 0.25. And so does C. So, it also has a probability of 0.25. Okay, so that probability shouldn't give anybody too much trouble. But what's the deal with X, decision content? X describes how often a yes or no decision needs to be made to arrive at the character. Each of these yes or no decisions is 1 bit. The longer it takes to make the decision, the longer the code for the character is gonna be. Okay, so here, let's check out this thing that looks an awful lot like a Huffman tree. This makes it really easy to determine the number of decisions that need to be made. For A, we'd only need 1 decision, that is, 1 bit. It only takes 1 branch to get there. For B, we'd need to make 2 decisions, so we'd have 2 bits for this one, since we'd be using 2 different branches. And it's exactly the same thing with C. So basically, decision content just describes how often a yes or no decision needs to be made in order to get to the character. The higher the probability, the fewer decisions need to be made. Or in even simpler terms, this is ultimately just the length of the code word for the character. And since no one wants to have to draw a tree each time, there's also a formula for X. All you need to do is figure out the log 2 of the inverse of the probability. So for the character A, we just put in 0.5 as its probability. Do the math and we get 1. That's the exact same decision content it had in the tree before. So to get the entropy, we need to multiply P times X for each character and then add it all up. For now, remember that entropy, Greek letter eta, describes the average decision content or information content of a character. P represents the probability of a character and X represents its decision content. Okay, now let's look at the term average word length and see what it means. It's usually represented by L and has the following formula. Now we're already familiar with the sum symbol and P. And the value of CA just described the length of a coded character. Let's assume the code for A is 0. The value of C would then be 1, since there's only 1 character in the code. B would then have a code of 10. And this would mean a value of 2 for C, since the code is 2 characters long. So to get the average word length, we'd need to get the probability of each character and multiply it by its code length, then add it all up. All you really need to remember here is that average word length describes the average length of all coded characters. Before we get to our little example, let's have a look at the term redundancy. Basically, redundancy just describes how effective a coding system is. The lower it is, the better the code works and the more effective the compression is. You can figure out redundancy, R, by just subtracting H from L. And that's what we need this L and this H for, to calculate how efficient our code is. Alright, so those are the most important terms. Now let's go back and look at our message from before. We're gonna go ahead and calculate its entropy, average word length, and redundancy. Here's what the formula looks like for entropy. And if you remember, here's what the probabilities for each character are. To get X, we need to use this formula here. Now if we do this for every letter, here's what that's gonna look like. Now we just multiply and add the whole thing. And that's how we get our entropy. Next is average word length. Here's the coding system we're using. The code lengths would be 1, 2, and 2. Then we multiply and add all this up again. To figure out redundancy, it's just L minus H. So you can see here that there's a redundancy of 0. That means the code doesn't contain any unnecessary information, which in turn means it's the best it can be. Now for larger coded messages, this all works the same way, but on a bigger, more complicated scale. And by the way, redundancy does not actually equal 0 in most cases. This is because entropy and average word length usually aren't the same, especially since the decision content is often going to have a decimal number. Oh yeah, and for images, the terms are pretty much the same, with the pixels actually functioning as characters. Okay, so what do we need to remember today? Entropy describes the average decision content of a character. Average word length determines the average length of a coded character. And redundancy lets us know how efficient a coding process is when it comes to compression. Phew! That was enough theory for one day, wasn't it? Go ahead and click on the next video to see how some of these are used in practice.